Hello and welcome to the presentation, Could Earthquake Early Warning be Effective Across Europe? My name is Gemma Cremen, I'm from UCL, and I co-wrote this presentation with my colleagues Carmine Galasso of UCL and Elisa Zuccolo of EU Centre. The purpose of this research is to investigate the feasibility of having earthquake early warning across Europe, where there's a clear need for measures that mitigate seismic risk. This need has been demonstrated by recent events like the 2020 Croatia earthquake and is also underlined by recent reports from worldwide organisations like the World Bank. It's also underscored by the fact that, on average, more than €20 billion of European GDP is affected by earthquakes each year. In this study, we focus in particular on current seismic stations across Europe and their ability to function as part of a regional or network-based earthquake early warning approach, accounting for the velocities of P waves and S waves that emanate from certain seismic sources across the continent. So in other words, we focus in particular on the highlighted section of an earthquake early warning system in this study. So the idea of this research is to focus in particular on high hazard area sources, which we define as sources where the event with a recurrence interval of 500 years has at least a magnitude of 6.5. And we specifically investigate target sites where these events produce a median predicted peak ground acceleration of at least 0.05 g. Now we also account for P wave and S wave velocity models, as well as the locations of current seismic stations, as mentioned previously. And we combine all of the information shown on the left-hand side to produce what is known as a lead time map for all target sites of interest, where lead time in this case is defined as the difference in time between when an alert is issued by the earthquake early warning system and when the strong ground motion arrives at the target sites of interest. Now, the map shown on the previous slide is what we can produce if we consider just one area source for each target site. But in reality, each target site is affected by a number of area sources. So what we can do is we can iterate across each of the area sources that affects a given target site, calculating a lead time associated with each of the area sources to come up with an overall lead time distribution for each target site. That can be summarized in a series of plots, like a minimum lead time map, which tells us the worst case scenario for each target site, a median lead time map, and a maximum lead time map, which tells us the best case scenario for each target site. And what we find is that almost half of all target sites benefit from lead times greater than 5 seconds in a best case scenario. Now, this of course is dependent on the magnitudes of the incoming events, as well as the ground shaking threshold above which an earthquake early warning is issued. What's more is that we can go one step further than simply considering lead times, but we can also consider the population that surrounds target sites and therefore would be exposed to incoming events that affect the target site, and also the average seismic intensity that each target site is exposed to from the events we particularly examine in this study, which is the events with a recurrence interval of 500 years from high hazard area sources. And combining all of this information together allows us to get a deeper and more informative picture on the overall potential benefits of installing earthquake early warning across Europe. Now, what we can do is we can summarize all of this information into plots like those shown on the slide here, where on the y-axis we have different proportions of the examined population that are exposed to average seismic intensities from the events that affect the target sites at which they're located. And then on the x-axis we have the lead times that these different proportions of the populations would benefit from across the 3 different lead time maps of interest. Now, the first thing to take away from these plots is that if we add up the y-axis of both plots, we'll find that about 98% of the examined population are exposed to average seismic intensities between strong and damaging, indicating that if earthquake early warning were to be installed to facilitate the target sites we examined, it would have the potential to contribute to reducing significant seismic risk at these target sites. The second thing to take away from this plot is if we look at the median and the maximum lead time bars in particular, we find that a notable proportion of the population has positive lead times in both cases, again indicating that earthquake early warning could potentially be effective across Europe. We can measure earthquake early warning feasibility at a particular target site in a formal way using what is known as the Relative Feasibility Index, which is a metric we developed as a synthesis of the information shown on the previous slide. This index contains three components: a population component, a seismic intensity component, and a lead time component. And each of these components are expressed in the form of a percentile. So for a particular target site, this percentile represents the ranking of the target site relative to all other target sites with positive median lead time. So the maximum value of the index for any target site would be 1, and this would occur for a target site that had the highest associated population around it relative to all other target sites with positive median lead time. It had the highest average seismic intensity associated with incoming events of interest at the area sources of interest, and it had the highest median lead time of all target sites. An interesting and valuable addition to this index is the presence of weights, which enable us to capture diverse stakeholder priorities and preferences towards each of the components of the index. So we can imagine that one stakeholder might be interested in installing earthquake early warning in an area that has a high amount of population, whereas another stakeholder might only be interested in installing earthquake early warning if regions around it would benefit from high lead times. And these weights that we've added to the index accommodate these different stakeholder ideas, preferences, and priorities towards the installation of an earthquake early warning system. So what we do is we calculate the relative feasibility index across all target sites with positive median lead time. And here we're showing the map that would occur if a stakeholder weights all three components of the index equally. And we can see that the most feasible sites for earthquake early warning are all located in either Italy, Turkey, or Greece. But what if lead time was instead prioritized by the stakeholders? Now, in this case, most sites with the highest earthquake early warning feasibility would still be located in Italy, Turkey, and Greece, but the exact location of the highest feasibility sites would slightly change. But what if seismic intensity is prioritized? Well, again, Greece, Italy, and Turkey are the countries with the highest earthquake early warning feasibility. And these countries would remain the most feasible for earthquake early warning if population was instead prioritized. So in conclusion, we've seen that almost half of all examined target sites could benefit from a lead time of at least 5 seconds in a best case scenario if earthquake early warning was installed considering current seismic station locations and a regional earthquake early warning approach. Now, of course, this conclusion is dependent on the magnitudes of the incoming events as well as the earthquake early warning ground shaking threshold set. The second conclusion we saw is if we combine these lead time maps with additional information, we found that earthquake early warning could ultimately be useful as a supplemental tool for mitigating the effects of large events on exposed populations. And this again is dependent on keeping delay times to a minimum. Thirdly, Across Europe, using our novel Relative Feasibility Index, we found that the most feasible sites for earthquake early warning are located in Italy, Turkey, and Greece. And you can find more information on this study in the publication shown at the bottom of the screen. Thanks very much for listening.